So this morning it was the Berkeley coffee that didn't arrive, and now it's the Berkeley laptop that can't connect to the Berkeley projector, so I concede, Stanford wins. But with that, yeah, so very excited to be here and very excited to tell you about our project, Autobahn, which is a new Byzantine Fault Tolerant consensus protocol that we published at SOSP last fall and that we've seen some sort of recent adoption in industry. Now, for those of you who don't know, Autobahn is the German word for highway. So the German highway famously has no speed limit. So when you think of Autobahn, I'd encourage you to think of a Ferrari going 200 miles per hour on the German highway and not on the Berkeley-Stanford congestion stretch. So with that, at a high level, Autobahn really strives to do two things. The first is that we aim to build a system that accounts for more realistic network conditions. So something that offers high performance, both when the network is behaving well, behaves gracefully, but also when it recovers from intermittent turbulence. And what we found is that networks tend to not be super well behaved in general. They're often quite blippy. The second is that we'll obviously make the case that thinking about BFT consensus doesn't need to be a dark art, and I'm sure you all agree with that, and that it can be simple. And that's paramount for building systems in production. Now, what I find funny about introducing this line is that the next 3 talks are also going to claim to have a protocol that is simple. So I'm going to say this is simple for my definition of simple. So let me, before we get started, let me briefly set the stage. So I don't think BFT needs a huge amount of motivation for this audience. So very quickly, just to clarify what I'm talking about, BFT consensus is at the heart of the blockchain stack and promises to implement the abstraction of a shared, totally ordered ledger, meaning that every participant orders the same set of operations and does so in the same order. And these guarantees hold even if a subset of participants misbehave. Here we're talking about n participants and f possibly arbitrary faulty nodes. Nothing special here. So BFT consensus has a hard job. It's a really nice abstraction to have, but you need to implement it well. And for it to be useful, it needs to have high throughput, it needs to have low latency, and obviously, as the name suggests, it needs to actually tolerate Byzantine faults. Namely, it needs to be robust to arbitrary network failures. And you have to do this while dealing with the troubling reality that our networking colleagues haven't yet figured out how to make the network synchronous. And famously, consensus is impossible in an asynchronous network. But obviously, that would make for a very short talk. So what do we do? Well, to deal with this, practical solutions that are deployed today look to partial synchrony. So in this model, we basically use timeout to approximate synchronous intervals and try to detect faults. So we're going to maintain safety at all times, but we're only going to offer liveness when synchrony eventually holds. And in BFT theory, this is typically modeled as something called the global stabilization time, or GST. And this is basically the period after which timeouts start holding. And now this model allows us to rigorously talk about what a protocol does, but obviously there's a big gap between the bookish version, where there is a point at which GST will hold forever, and what we deployed in practice. And current systems have to deal with the practical reality today. So in practice, this rosy reality of ever holding synchrony is, of course, a fiction. And, current protocols recognize that. Missed timeouts are common and can trigger for huge kind of behaviors, ranging from DDoS to network delays to simple replica failure. Now, the cause of those events doesn't necessarily matter for our use case, so I'm going to bundle them under the umbrella of something called a blip. Now, a blip is anything that temporarily interrupts the progress of consensus and requires us to take action to recover. Now, something that I want to emphasize here is that these blips aren't fringe cases. Instead, as the name partial synchrony suggests, blips are the common case because synchrony is truly partial or periodic. And this means that to claim good performance, a partially synchronous system needs to perform well both in the absence of blips as well as during their resolution. And this is really the problem that we're going to target today. So existing systems don't handle this disconnect super well. So if we take a simple experiment with Hotsoft, one of the most popular BFT protocols today, we're going to simulate a blip caused by a single replica failure. And we're going to run the experiment with this fixed input rate close to the system peak throughput. And the graph is going to show latency relative to its start time. So, latency of transaction commit relative to its start time. So during the blip, hot stuff is going to make no progress, and as a result, the incoming requests are going to form a backlog. Once the blip resolves and the progress resumes, this backlog needs to be worked off. But you can only do so, you can only work off this backlog as much as the excess resource capacity allows you to do so. And this is going to result into a performance degradation that is actually going to last well beyond the resolution of the initial blip. And we're going to call this problem a hangover. This is the effect of trying to recover from a blip. Now, I think everyone's going to agree that hangovers, whether it's in real life or in consensus protocols, are undesirable and we want to avoid them. And ideally, we'd like to tolerate a blip very much like this. During the blip, we're going to continue to lose progress. That means that transaction latency is going to increase. But once the blip ends, we're going to immediately make up for all lost throughput and return latency to normal. Now, we're going to call protocols that achieve this property seamless. A seamless partially synchronous protocol should fully avoid hangovers, and perhaps obviously it should do so without cheating and simply killing liveness altogether. So in particular, we're going to want to develop seamless protocols that do not produce more blips in the process, because otherwise that defeats the point. So on that note, let me introduce Autobahn, which promises to satisfy all the sort of tough demands that we expect from BFT, as well as seamlessness. Autobahn wants to achieve high throughput, low end-to-end latency, and seamless recovery from blips. And an orthogonal goal that we pursued while looking at Autobahn was that we wanted the design to be not just simple, but also modular, meaning that you can actually plug in your favorite BFT protocol in Autobahn's architecture to give it high throughput and makes it seamless. So for whatever reason you're currently deploying hot stuff, for example, you can combine hot stuff with Autobahn to add seamlessness to hot stuff, or replace hot stuff by any BFT protocol you choose. So let me talk about how we do this. At a high level, Autobahn is going to consist of two core components. The first is going to be a data layer that transports batches of transactions at the pace of the network, regardless of interruptions to consensus. And the second is the consensus layer that is going to consume this data layer and reach agreement on its output. Now, separating the data layer from the consensus layer is a well-known idea, and that's not the main contribution of our system. Rather, our challenge lies in finding the right balance and coordination between the two layers. If we offer too few guarantees, then we'll end up with something that is not more seamless than any existing protocols. But if we lump them together, then this is going to come at a significant performance cost. So we really wanted to find the right balance and the right level of interplay between the data layer and the consensus layer to achieve seamlessness, while preserving high throughput and low latency. So what we settled on is that to support seamlessness, our data layer needs to have three key properties. So first, we obviously need to make sure that our data can be reliably retrieved. And that requires us to ensure that at least one correct replica has stored the data. Otherwise, Byzantine replicas can cause us never to recover the data. That's not surprising. In order to avoid hangovers, we also want data dissemination to make as much progress as possible, namely at the pace of the network. And I'm going to call this property responsive data dissemination. And finally, we want to be able to easily index or disseminate data so that arbitrarily, independently of the amount of data that has accumulated and has been disseminated, consensus can easily index it and order it all at once. So that's the three properties that we're going to want from this data dissemination layer. Availability, responsive dissemination, meaning that you make progress at the speed of the network always, and this instance referencing property that consensus is going to use to quickly recover from blips. So let's start at the top. The key unit in Autobahn's data layer is a car, which is just a fun way of describing the process of guaranteeing the availability of requests. A car starts with one replica that acts as the proposer, and that proposer is going to broadcast a batch of transactions to everyone in the system. Other replicas are going to store this batch and return a vote to acknowledge that they have stored the data. Once the proposer receives enough votes to ensure that at least one correct replica has stored the batch, it can prove to others using this car certificate that this batch is truly available. Nothing fancy going on here. One thing to highlight, though, is that cars do not provide any stronger guarantees in data availability. Specifically, it is possible for cars to equivocate. That's okay. And the reason for why that's okay is the data layer should be concerned about dissemination, not ordering. What this does is guarantee data availability, and that keeps the decoupling between consensus and data dissemination very clean. Now, once we have cars, we're going to change them together, just as others have done in the past, into what we call a lane. Specifically, each new car that a proposer creates is going to contain a hash reference to the previous car it created, which implicitly is going to create a total order within a lane. Now, this chaining property is going to allow us to uniquely identify and prove the availability of the entire lane with just the last car. And this is what gives us our instance referencing property. Specifically, because you're including the set of hash references, as long as you have the final tip of the lane, then you know that all previous blocks that were in that lane are also available. And that will give us our instance referencing property. And we care about this because of seamlessness, because we're going to leverage that property to allow consensus to commit long lanes very fast with just using the first car. And we can do so at a cost independent of the length of a lane. Finally, we're going to take the concept of a single lane and expand it so that every replica governs its own lane. Specifically, each lane is going to grow independently of other lanes and without timeouts. Now, having multiple lanes maximizes the throughput and guarantees that dissemination does not hinge on a single proposer. And because that's a problem, because that single proposer might be malicious. Running them independently is then going to minimize coordination and allow us to flexible proposer speeds, which can be good if you have heterogeneous validators, for example. Now, lanes guarantee a responsive dissemination property, and we care about this seamlessness because we're going to continue growing our lanes even when consensus cannot make progress, as long as data can still go through. Now, usually we get a question here that says, well, what if there's a network partition and data can't go through? Well, there's nothing we can do here. But what we found is that during blips, there's often cases where data can make it through, and there's a progress interruption because of a leader failure, or because there's a partition that doesn't partition the network fully in the middle. So there's a lot of cases where data is still being disseminated, it's just consensus cannot make progress. Okay, so this is how we structure our data dissemination layer. Now we can move on to consensus. So let's first try let's just take a look as to why we even still need consensus. Well, remember that our data layer only provides fairly weak guarantees. And that means that asynchrony or equivocation can cause lane states to diverge between replicas. For example, two replicas here, they don't need to necessarily have the same lane state. So specifically, if you look at the third lane here, replica 1 has 2 blue cars, while replica 2 has nothing. In contrast, if you look at the orange lane at the very bottom, the first replica has seen 4 cars, while the right replica has seen 3 cars and a truck. And that can happen because our lanes, by design, do not guarantee non-equivocation. So we need consensus to be able to reconcile divergent lane state. And this is where the instance referencing property is going to come in handy. So remember that because of instance referencing property, we can uniquely identify an entire lane from just the last car alone. So instead of reaching agreement on cars individually, we're simply going to propose a snapshot of our data layer by using the last car, or the tip, of every lane. So in the example here, the snapshot would be, the tip cut would be green car 2, red car 2, blue car 2, and orange car 3. And this simple TIM cut is going to transitively prove the availability of all preceding cars. And in particular, this means that the size of our consensus protocol is going to grow as a function of the number of lanes, but is going to be always independent of the size of the backlog, which is vital for guaranteeing seamlessness, because that's what we want to immediately commit any backlog data that arose during a blip. So tips give us succinct snapshots, and that's great. Now let's just say that we propose this tip card here. So the obvious question is, when should you create new tip cuts? Now ultimately, consensus works on data. There's no point in doing consensus on data that you don't have. And so we're always going to want to make sure that we do a new consensus instance when there's new data to propose. Now, obviously, because some lanes might be malicious up to F, we don't want to wait for all lanes to have new data. So the halfway point that we found is that we're going to propose new tip cuts when you have n minus f lanes that have new information. Why n minus f? Because this guarantees that a majority of new data comes from honest proposals. But this is configurable. You can configure it to account for different bandwidth between lanes, reputation schemes, so on and so forth. And we have lots more details about that on the paper. So you'll notice that I'm slowly running out of time, and I haven't mentioned how we reach agreement. Now, I'd love to sort of tell you more about the specific protocol that we use, but I don't have time to go into details. So learning about it is one of the many pleasures you'll get by reading our paper, hopefully, or the many headaches, depending. But you can very much think of it as a pretty standard PBFT protocol. We have an option for it to be linear, so like SBFT, or we can be quadratic, like PBFT. And what I want to point out instead is a couple of sort of features that I find cool. The first is that our data synchronization subprotocol takes advantage of our lane structure to provide the guarantee that you can fetch missing data in just a single round trip. Now, obviously, if you have to download 10 gigabytes of data, that's still going to be slow, but you can identify where the data is in a single round trip. The second benefit that we have is that there's a number of additional optimizations that we do to minimize latency. So this includes, amongst other things, a commit fast path and pipelining, such that when you take the quadratic version of the consensus protocol, we can have optimal message latency. So we can have 3 message delays in the good case when you have the fast path, and 4 message delays when you go slow path. Add a couple of extra message delays if you want the linear version of PBFT. And the last aspect is that just because I'm saying you can switch PBFT and from linear PBFT to quadratic PBFT, we can actually keep the system modular, meaning that we can instantiate the Autobahn framework with multiple consensus protocols. So you can use the same lane structure and run PBFT. You can use the same structure and run SBFT or others. And that was by design. We wanted to very much separate the data dissemination layer from the act of agreeing on tip cuts. The last aspect is execution, and that's nothing very challenging here. So once a tip cut becomes committed, replicas can commit and order all cars and the transactions that precede the tip cut. So how do you order the cars? Well, that's not a very hard thing. Because everyone agrees on the same tip cut, that you can use any deterministic function to interleave the various lanes with respect to each other, come to the conclusion of the same total order, and then execute it. You can execute it using the whatever execute engine you might want. So before I end, just want to show you some brief experimental results. So we evaluated Autobahn against protocols in 2 categories. So the first is, I would say, the traditional star BFT protocols, like Hotstar, for example. So they have really good latency, but they do not separate data dissemination from consensus, and as a result, as we showed already, they struggle with seamlessness. We also evaluated a variant of Hotstuff that tries to naively separate data dissemination from consensus, but this design also doesn't guarantee seamlessness. Now, I'll call those vanilla Hotstuff and batch Hotstuff, respectively. The second class of protocols that we looked at is Borchardt. And that's a state-of-the-art protocol for achieving high throughput specifically, and it sort of descends from the family of DAG BFT protocols that have become popular in recent years. And those are almost seamless, but not quite. And I'll leave that as an asterisk. Feel free to, we can discuss this offline. But from the point of view of this talk, I'll just consider them as seamless. And those achieve high throughput, but struggle with achieving good latency. So onto the numbers. For our first experiment, we showed a throughput latency graph. And we do this in an ideal fault-free scenario. So a throughput latency graph, for those of you who aren't familiar, works like this. You increase the number of clients. This increases the throughput that your system has, which is what's growing up on the right. And at some point, you're going to hit saturation, which is going to cause latency to spike up. And so the number that matters is the number before latency starts to spike up, which is the peak throughput that you can get, and that's the latency that you'll have under stable conditions. So Autobahn, shown in green, is able to match the throughput of Borchardt, shown in blue, while also having latency that is comparable to hot stuff. And compared to Borchardt, this means that Autobahn's latency is over 2 times better without making sacrifices in terms of throughput. Most importantly, Autobahn's pitch was not just about performance, but it was really about recovery from blips. And since we already showed you that how hot stuff deals with a replica failure earlier, let's just quickly revisit this example with Autobahn. So we had a leader failure. We increased the blip duration slightly, but the takeaway remains the same. Hot stuff in blue is going to suffer from a significant hangover, which is even longer than the blip duration, because it did not optimize for seamlessness. In contrast, Autobahn, shown in orange, returns to the baseline latency immediately as promised, aka immediately as the blip ends. And so we are able to achieve seamlessness. So that brings us to the end of sort of the Autobahn overview. So I want to briefly summarize. So Autobahn shows us how to build a BFT system that is not just efficient under partial synchrony, in theory, but also in practice. It matches performance of existing BFT protocols, but has much better robustness. And what we like is that it's simple, meaning that you don't need to start from scratch, but you can already build around the core that you already have. Now, Autobahn has been adopted in production by a number of companies, which we're pretty excited about. Say Commonwealth Order Broadcast, Hangovers, Inform Insomnia Chain, Hiller. So if you're thinking about what consensus protocol to pick, we'd love to chat, and we'd love to see how we can moderize your existing consensus protocol rather than tell you how to replace your existing consensus protocol. So if you have any questions, we'd love to chat more. Neil, who is one of the lead PhD authors, is in the room here. Florian is available remotely. If you don't have any questions, but you want to give Neil an academic job or an industrial research job, just talk to him anyways. But thank you.
So if you're waiting for every lane to have at least one new transaction before you do a cut, couldn't this get inefficient if some of the replicas either don't have new transactions to offer, or if they're all offering the same transactions, so you have a huge amount of redundancy across the lanes?
I think at the end of the day, so I'd say there's 2 issues. There's the issues of duplicate transactions that we don't solve, and as far as I know, that's a problem in most systems unless you try to, before submitting the transaction, do some amount of deduplication. That is a problem here. The second part of the question is that this is configurable. So it is perfectly fine to say that I'm going to do consensus every k unit of time, and that is going to confirm that the lack of progress is important. You can do it optimistically if you think that you trust the lanes have been reputable, and you can do it as soon as you have one more element. It's a completely configurable parameter, so whatever works for your system.
For the car, to chain it, do you have to give the certificates of the last one back to the next people to verify that and then give you attestation back, or how does that work?
Yeah, so the proposals includes the
proposer includes the last certificate.
Yes.
To the next proposal.
So each each lane is one validator.
Uh-huh.
And so when you do when you create a car, you include a reference to the previous car. And the certificate that you have from the previous car.
I see, thank you.
I'm just wondering if there's any particular reason that you didn't choose to compare with dispersed ledger that has the same idea of separating data dissemination using VID from consensus, making it leaderless so that each node can disseminate its own data, and also I think the lane aggregation idea, which is basically for each person to disseminate their own data, but having a consensus only for agreeing on like progress across the board, like the envelope of dissemination progress. I think the only difference I perceive, since I'm a co-author, is that dispersed ledger is in the asynchrony setting.
Yeah, so it's a fast-moving space, and so we try to do a good job by comparing against representative style protocols. Specifically, that's why we picked Hot Stuff on one and Bullshark on the other. I also think it was very, if I remember correctly, almost concurrent work, so we didn't have the thing available.
It's NSDI 2022.
Yeah, so I think by the time that we were building Autobahn, it was like this. And I think we made the decision to just have partially synchronous protocols as a way to make a clean cut.
Yeah, makes sense.
All right, maybe we can postpone the remaining questions. We thank you very much, Natacha, first of all.